This is 11.4 Fundamentals of Probability. Now, in real life, most of us have already heard or seen examples of probability. For example, you may think of the weatherman and the percentages or chances of rain. We have an 80% chance of rain today. That percentage, which is what is normal for most of us to look at, is to think of a probability in a percentage. And if you look at the very top of this bar, we have this 100%, then midway is 50%, and then 0%, or equivalent to, and if you look at the integer here, we have 1, 1/2, or 0. So when we think of probability, it actually is a number between 0 and 1. 0 meaning that the event or the probability of something occurring, it will not occur. If it is a 1, it is definitely going to occur with certainty. All right, so you can see the little different definitions at the very top. At 100%, it has certain. Then we go to likely. We have a 50-50 chance in the middle, unlikely, and as we approach the 0, it's impossible or not going to occur. So once again, that probability will fall between 0 and 1. So most of the time you'll see it written as a fraction, but it can be written as a decimal. So read your instructions carefully to see how they want that probability presented. Your probability can be 0 and it can be 1, but everything in between. All right, so the definition of probability is the likelihood that an event will occur under a set of given conditions. Computing theoretical probability. If an event E has cardinality E, equally likely outcomes, and its sample space S also has equally likely outcomes, the theoretical probability of an event E is denoted by P of E. So this P of E right here means the probability of the event E. So notice we have in the numerator the number of outcomes in event E over or divided by the total number of possible outcomes. All right, and if this very end part should remind you of chapter 2, the cardinality of E divided by the cardinality of the sample space. The outcomes for each, the cardinality of E, the cardinality of S. So let's take a look at some of the definitions here. Sample space, the set of all possible outcomes of an experiment. Event, any subset of a sample space. Boy, chapter 2 is coming right back to us, isn't it? All right, so let's look at this example. Right in the middle, it says S is equal to, and it says HT. So in this case here, I would define my event, and I'll just call it E, as tossing a coin. All right, so my event E would be tossing a coin. My sample space is that it could be H for heads up and T or T for tails up. All right, in this case, since the coin has two sides, we can say theoretically it is a 50-50 chance of landing on heads or tails. All right, so theoretically, we're looking at you have two options, heads or tails. You have a 50-50 chance or 50-50%. All right, so let's look at our first problem. It says a die is rolled once. Find the probability of rolling A, B, C, D, and E. So we're going to look at each situation and see if we can find the probability. The first thing we need to realize is about a die is that it has 6 sides. And with those 6 sides, our sample space, we'll call it S, we can roll a 1, a 2, 3, 4, 5, or a 6. So it is a 6-sided die, and our sample space is 1, 2, 3, 4, 5, and 6. All right, so let's take a look at A. A is asking us for a probability of rolling a 3. So we put probability of a 3. So when we're looking at the probability of rolling a 3, we're looking at all the possible ways of rolling a 3. Remember the cardinality of event occurring divided by the cardinality of the sample space. So how many 3s do we have in our sample space? We have 1. And how many elements do we have in our sample space? We have 1, 2, 3, 4, 5, 6. We have 6. So the probability of rolling in a 3 would be 1/6. And this meets our requirement of having a probability value that falls between 0 and 1, inclusive of 0 and 1. All right, for B, it says, what is the probability of rolling an even number? So I'll just write down probability of even number. Once again, we need to remember we have the event of an even number, so I'll just put it as roll an even over the total. So how many even numbers do we have? We have 2, 4, and 6 in our sample space. So there are 3 even numbers over the total number of elements in our sample space, which is 6. And then we have to reduce our fraction, always simplify. And our answer is 1/2. So the probability of rolling an even number is 1/2. Then we'll look at C, the probability of rolling a number less than 5. Right? So we're going to take a look at our sample space and find out how many numbers are less than 5. So that would give us less than 5 would be 1, 2, 3, and 4. So there are 4 numbers less than 5 over our sample space, 4 over 6, which reduces to 2/3. All right, and then part D, a number less than 10. Less than 10. So I'm going to use that less than symbol. So let's take a look at our sample space and see how many numbers are less than 10. Well, all of them are less than 10, so that leaves me 6 numbers are less than 10, divided by the number of elements in my sample space, which is 6. And 6 divided by 6 is 1. So remember, 1 is equivalent to 100%. So there's a 100% chance of rolling a number that's less than 10 if we roll our 6-sided die. All right, and then we have E. And E says, what is the probability of a number greater than 6? Number greater than 6. So we look at our sample space and we ask how many numbers are greater than 6? Well, there is 0 greater than 6 divided by the number of elements in our sample space, 6. 0 divided by 6 is 0. So there is a 0% chance of rolling a number greater than 6 on a 6-sided die that contains the numbers 1, 2, 3, 4, 5, 6. So once again, we're going to keep an eye on our sample space here. It's always helpful to identify that. All right, and I'm just going to clean this up a little bit so you can find each of my items. So for this problem, we are revisiting the 52 card deck. If you take a look at the diagram here, once again, we have 4 suits. We have hearts, clubs, diamonds, and spades. And each of these suits has 13 cards. The first one they start with is an ace. And we have 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we go to jacks, queen, and kings. So each suit, there's 4 suits containing 13 cards. All right, so let's take a look at our problem here. It says you are dealt one card from a standard 52 card deck. So you get to pick one card. Find the probability of being dealt a king. All right, so remember, your sample space is this entire deck of cards right below at the bottom of the screen here. If we want to get the probability of selecting a king. So when we're looking at the probability of king, remember we're looking at the total number of possible outcomes for just picking a king. So the first part we're going to take a look at is what is the number of kings we have. Number of kings divided by the total number of cards. All right, so in this case here, if you take a look at our suit, at the very end of each of these, we have a picture card for king, and we have 4 kings. We have a king of heart, king of clubs, king of diamonds, king of spades. So there are 4 kings. Now that is divided by the total number of cards. So we have a total of 52 cards. And again, you always want to reduce your fraction, and we reduce this to 1/13. So the probability of selecting a king from a deck of cards is 1/13. All right, let's take a look at part B. It's asking for a probability of a heart. Probability of selecting a card that is a heart. So we want to know the number of hearts that we have to choose from over the total number of cards that we can select from. Our sample space is the entire deck of cards. So once again, we have 13 hearts over 52 cards to choose from, and we reduce this and it becomes 1/4. This is the probability of selecting a heart. All right, and the last one is the probability of a king of hearts. Right? The probability of selecting the king of hearts. So in this case, we want to know how many number of king of hearts do we have. Divided by the total number of cards we have to choose from. If you look in this deck of cards, we have exactly 1 king of heart right here. I'll circle it in yellow. Out of 52 cards. So we have 1/52 likelihood of selecting a king of hearts. All right, so for this problem, it says a single die is rolled. The 36 equally likely outcomes are shown to the right. Okay, the single die is rolled twice. Excuse me, it's twice rolled. So if you see this ordered pair where it has a number, comma, another number, the first number is the first roll. Let me just write that down. It's the result of rolling the first die once. And then when you roll it again, you have your second roll here. So for instance, up in that far left-hand corner where it says 1, comma 1, I rolled a 1 on my first attempt, and then I rolled a 1 on the second roll. So 1, 1. All right, and it says on here, find the probability of getting two numbers whose sum is 11. So let's write that down. Probability of two numbers whose sum is 11. All right, so you have to think of the numbers that we have on a die. Remember, our sample space is just the entire 36 rolls here, but you have 1, 2, 3, 4, 5, 6 as far as that sample space specifically for the die. And the numbers that add up to give you 11, I will circle them here. We have a roll of 6, 5 and a roll of 5, 6. All right, you need pairs of numbers to add to be 11. So in this case here, you're going to have, this is going to be equal to, I have 2 out of 36 options. There's two ways for me to select a sum of 11, which would be 6 and 5 or 5 and 6, and out of 36 outcomes. All right, now these can be reduced a little bit further. So once you reduce it, you're going to get 1 over 18. All right, so again, we looked for the sum of 11, the probability of getting 11. There's two ways to get an 11, 6 plus 5 or 5 plus 6 out of the 36 equally likely outcomes. Computing empirical probability. It says the empirical probability of an event E is the probability of the event E is equal to the observed number of times E occurs, this is observed, over the total number of observed occurrences. All right, so that you can distinguish the difference between theoretical versus empirical. Remember on our theoretical probability, we had a sample space for tossing a coin. We'll say event E is the toss of a coin. And our sample space gave us heads is up or tails is up. All right, theoretical. All right, so theoretically, we know that it has two sides of this coin. So there is a 50-50 chance of getting a heads or a tails. All right, but empirically, on the empirical probability, it is conducted through observations. So once again, we may be tossing a coin, but our experiment may be tossing a coin 10 times. All right, so what happens when they say observe, we're going to observe someone tossing a coin and we'll record the results of what is turned up, whether it was a heads or whether it was a tails. And again, our sample space is still the same. It is still heads or tails. We will record and observe how many times we've seen heads, how many times we've seen the tails. Now, if we're only tossing 10 times, which is not very much, there's a pretty slim chance that we'll get 50-50 to come out of those 10 attempts. But the more that you increase the tossing of the coins, maybe we increase it to 100 times we're tossing coins or 1,000 tosses of the coin, the more we increase the number of times we toss this coin, we will become closer and closer towards that theoretical of having a 50-50 chance of getting a heads or a tails. So that is the difference between theoretical is that it actually is two-sided 50-50. Empirical was going to tell us our probability is recording the observations and finding out exactly what is the probability. So we are limited to how many observations we record. For this last problem, it gives us a table here and it reads the probability that a randomly selected single parent in the US military is in the Army. So what I'm imagining is that since this doesn't have a title to it, that the title would be Single Parent in the US Military would be the title of this table so that we can use the table in its entirety. All right. The instructions also say to type in an integer or a decimal rounded to the nearest hundredth as needed. All right. So the probability that a randomly selected single parent is in the Army. So we're looking at the probability that single parent is in the Army. Let's take a look at our table and see if we can find the number of these parents. Remember, these are all parents that are listed on here. The number of parents that are in the Army, and that would give me 38 out of the total number in the military, and that would be 98. So we have 38 divided by 98. And our instructions did not say to enter a fraction. It says type an integer, which this fraction is definitely not an integer, or a decimal. So we are going to place this in our calculator. And it looks like we have 0.3877. I'll just carry it out a little bit. And it says round to the nearest hundredths. We're going to go find that number that's in the hundredths position, which is this 8. We look to the right to see if we have 5 or larger. 7 is greater than 5, so I'll add a 1 to this hundredths position. And then my final rounding would be 39 hundredths. Right, so the probability of a single parent that is in the Army is a decimal form, 39 hundredths, or 39% if you'd like to see it that way. This concludes your lecture on 11.4.